In this segment I will give a brief introduction to the task of part-of-speech tagging, and then we'll come back and see how discriminative sequence models can be used as a technique for part-of-speech tagging. There are many linguistic traditions in different parts of the globe, but in the West the idea of parts of speech perhaps started with Aristotle and in the 4th century before the Common Era, and he suggested the idea that there were parts of speech which are otherwise known as lexical categories, word classes, tags, or POS is a common abbreviation. But what we think of today as the parts of speech are normally attributed to Dionysius Thrax of Alexandria, who proposed that there were 8 parts of speech. And that's the number that's still with us today as the number of parts of speech people get taught in school sometime. Though actually, if you look into the details a little, the 8 parts of speech that Dionysius Thrax proposed aren't the same that are with us today. So the normal list that people are taught in schools in English now are noun, verb, adjective, adverb, preposition, conjunction, pronoun, interjection. But for Thrax there was actually some little differences in the list, and of course he was working with ancient Greek and not with English. So the beginning of the list starts out the same, but note that he doesn't recognize adjective as a part of speech. In Greek and Latin, adjectives and nouns behave very similarly, but he does recognize participle as a part of speech. And then the other difference is that a separate part of speech is given for articles, words like the and a, whereas in the modern list you get a class for interjections. The status of articles has always been a bit controversial. In our current standard set of 8 parts of speech, articles are seen as a case of adjectives, but actually as soon as you start looking at the grammar of languages like English, that the articles have a very special behavior which is quite different from regular adjectives. For example, adjectives you can get multiple of: large green leather couch, whereas you can't do things like this book, except as a kind of speech hesitation as to which article you should be using. When we do part of speech taking in computational linguistics, we normally work with rather more than 8 parts of speech, because there are a lot of distinctions which can be useful to make, and that multiplies the number of parts of speech. And so I start to indicate the kinds of parts of speech you get in this slide, and you can see that there are various hierarchical groupings. So inside nouns we can divide into proper nouns and common nouns, and we might also want to divide between singular and plural, which can happen with both proper and common nouns. Verbs very much divide into main verbs, C registered, versus various auxiliary and modal verbs like can and had. There are adjectives and adverbs. Note that adjectives, at least the short adjectives in English, have several forms: the positive, comparative, and superlative, and we might want to distinguish those forms as well. Neither of the lists on the last slide had numbers, but they seem a fairly obvious and practically useful part of speech to recognize. And then similarly here among the closed classes, I'll say a bit more about closed classes on the next slide, we don't have a category that's called articles, we have a category called determiners. So the modern linguistic tradition is to group the articles a and the together with certain other demonstratives that behave similarly, words like some, this. And then we have some other categories. Prepositions are familiar, but we're distinguishing off a class of particles. So the particles here are words that are normally the same as prepositions, but take part in English phrasal verb constructions. Things like made up, meaning to invent. The top level distinction on the last slide was between open classes and closed classes. It's very clear that not all parts of speech are the same. Some of them, like determiners and pronouns, are occupied by only a small set of words. So in English for pronouns there's he, she, it, him, her, and the first and second person pronouns, I, you, we, third person plural, they, them, but it's just a very small set of words, and that there aren't new pronouns being invented. And so things like that we call closed class, because in general closed classes don't get new members. Though, you know, sometimes occasionally they do over long-term language change, so sometimes people have suggested that we should be inventing some new gender-neutral pronouns in English, though nothing's really taken off. But in contrast, the open classes, nouns, verbs, adjectives, adverbs, these are classes which have a vast number of members, and beyond that it's very easy for them to gain new members, so that when we have a new protocol in computer science, we create a new noun for it, like SSH, and then very quickly we decide it's useful to use that as a verb as well, and then we say, I SSH'd in to my server to fix the configuration. The task of part of speech tagging is to say for each word what its part of speech is in the context of some running text. The reason why that's not trivial is because lots of words have more than one part of speech. So for example, for the word back, it can be an adjective when it's modifying a noun, like the back door. It can be a noun when it's referring to the body part, on my back. It can be an adverb in a phrase like win the voters back. And it can also then be a verb in another political example, promise to back the bill. And so what we're wanting to do is, when we see an instance of the word back, assign it to one of these parts of speech. So in the task of part of speech tagging, we start with some text, plays well with others, and then for each word we consider what are its possible parts of speech, so that plays can be a plural noun or a verb, well can be an interjection, an adjective, a noun or an adverb. With is just a preposition here, and others is a plural noun. And so for the words that are ambiguous, we're then going to choose for them what their correct part of speech is in context. And so here, plays is a verb and well is an adverb modifying plays, and we get disambiguating these parts of speech. So what we're finding here at the end, when we've got these choices here, which we're then determining, these are our part of speech tags. And depending on the part of speech tag set, they're commonly in natural language processing applications somewhere between 12 and 100 part of speech tags that are differentiated. And so you can see that this set of part of speech tags is differentiating things like, is it a plural noun or a singular noun? Here's a singular noun. Or if it is a verb, what form of the verb it is. So this is the third person singular, plays, as opposed to play. So the particular part of speech tag set that we're seeing here is the Penn Treebank part of speech tags, which are the most commonly used part of speech tags for English, especially in the United States. I'm embarrassed to say that I've been in this business long enough that I can actually tell you off by heart what all the Penn part of speech tags are. There are a set of 45 of them, which cover word classes like this and punctuation. So what good is part of speech tagging? As well as letting you answer your high school English problems, it has a variety of other uses. It has some particular uses where just parts of speech are sufficient, so that if you're doing text-to-speech and you see an instance of the word lead, you want to know whether to pronounce it as lead or led, and the answer to that is, well, what's its part of speech? If it's a verb, it's lead. If it's a noun, it's led. Having parts of speech let you easily do some surface linguistic analysis. So for lots of applications, it's useful to pick out what we call base noun phrases. So they're a noun or noun compound, possibly modified in front by a determiner and some adjectives. So the nearest school or an old green couch are base noun phrases, whereas big complex noun phrases with relative clauses after them aren't. If we have parts of speech, we can easily write regular expressions that pick out things like base noun phrases or verbs followed by a particle for phrasal verbs. And that can be used for a lot of applications where you want to do shallow processing, but nevertheless want to be able to give to the user multi-word keywords or something like that. Part of speech tagging is commonly used as input to or to speed up a parser. So quite a few parsers work on already part of speech tag set text, and even ones that can do their own part of speech tagging can often be sped up by first doing the process of part of speech tagging. Finally, a lot of models we build for probability estimation are very sparse if they try and work at the word level, and we discussed various ways of backing off, where you might back off from a trigram to a bigram earlier. But another common way of backing off is to back off from a word that you don't know much about to its part of speech category. You can predict based on knowing it's an adjective. Part of speech tagging performance is normally measured as accuracy. What percent of tags do you get right? And the answer to that for the best current taggers, they get about 97% of words right. That sounds really good. It is important to realize that part of speech tagging is in some sense an easy task, or at least a task where you get high numbers. So there's a baseline approach to part of speech tagging where you tag every word with its most common tag if you know about it in your training data, and if you don't know about it in your training data, you tag it as a noun. And it turns out that that fairly simple baseline method already gives you performance of 90%. And so it turns out that you get this high baseline for a couple of reasons. One reason is that many words are unambiguous, that if you see famous, it's always an adjective. And also the way part of speech tagging is normally measured, that you get points for every token. So not only do you get points for every instance of unambiguous articles, which are very common, like the and are, you even get points for getting the part of speech tags of punctuation right. But that doesn't mean that all parts of speech decisions are easy. Some part of speech decisions are quite difficult, even for human beings. And so here are some examples of the word around. So here we have around acting as a particle, got around to. Here we have around again straight after a verb, but this time it's this prepositional phrase around the corner. And so around is being a preposition. And here again in this third example, around is again following straight after a verb, but actually this time it's a modifier of this noun phrase of around 250, short for around $250. And so around is then an adverb. It's modifying a number, which is kind of like an adjective. It turns out that in English corpus, around 11% of the word types are ambiguous with regard to part of speech. That doesn't sound like very many, but most of them tend to be common words, such as the word that. So that can be a word that introduces a subordinate clause, and in the Penn Tree Bank those words are tagged as IN preposition, which might surprise you. There's some linguistic argument about that. It can be a determiner, that play, or it can be an adverb. So modifying here far, that far is an adverb. And so it turns out that although only 11% of the word types are ambiguous as to part of speech, about 40% of the word tokens are ambiguous. So there actually are a lot of decisions for a part of speech taker to make.
So this slide shows a tagging problem called part of speech tagging, which is a very important problem in natural language processing and is actually one of the very earliest problems considered in statistical or machine learning approaches to NLP. Statistical models for this problem go back to the late 1980s. So the problem is as follows. As input to the model, we have some sentence, some sequence of words. And as output, we have a tag sequence. What I mean by that is that in this output from the model, each word is now given an associated tag. So profits, for example, has the tag N, which if we look at the key stands for noun. Sword has the tag V, which from the key means a verb. At is a preposition, that's a P, and so on and so on. So the task is to take a sentence as input and to word by word assign a part of speech to each word in that input. So why is this in any sense a challenging problem? Well, it turns out that ambiguity is going to play a crucial role in this problem, as it does in many other problems in natural language processing. So let's look through the words in this sentence. If we take profits, for example, it's certainly a noun in this context, but profits can, of course, also be a verb in English. So if I say the company profits from its endeavors, profits is a verb in that context. Let's look for some others. Topping is a verb in this particular sentence, but it can also be a noun. If I say, for example, the topping on the cake. Forecasts is a noun in this sentence, but it can also be a verb. Quarter is a noun, but it has a much less frequent usage where it can also be a verb. Results is a noun, it can also be a verb, and so on and so on. So as a rough estimate, you might find that words in English, on average, can take 2 or 3 possible parts of speech. And this isn't only true of English, it's true in many other languages, probably most languages in addition to English. So here is a second example of a tagging problem, and this is the problem of named entity recognition. Again, this is a very important problem in NLP, and actually in the first programming assignment for this course, you will build a complete named entity recognizer, so you'll build a model for this task. So what is the named entity recognition problem? The problem in this case is to take, again, a sentence, a sequence of words as input, and now in the output, we're going to identify named entities in the input sentence. So a named entity might be a company, or a location, or a person. Those are 3 very common entity types. And in this output, we've identified Boeing CO as a company, Wall Street as a location, and Alan Mulally as a person. So basic problem, take a sentence as input, and mark up all the entities in that sentence in the output. So again, this is a very basic problem in NLP, and it's useful in a wide range of applications. You can imagine all kinds of cases where identifying entities would be a useful task. Now, at first glance, this doesn't look like a tagging problem, because a tagging problem needs to assign a tag to each word in the input. And here we really have a segmentation, an identification of subsegments of this sentence. But on the next slide, I'll show you how we can map this problem very directly to a tagging problem. So how does this work? What I've basically shown you here is the same example again, but where I've represented the segmentation I showed you on the previous slide as a word-by-word tag. So we have various tags. NA stands for something that is not part of an entity. So if you notice, we've tagged every word in the sentence in turn, and several of these words are NAs. They're not part of an entity. And then for the company entity type, I have tags corresponding to the start of a company and the continuation of a company. So if we look at Boeing CO here, we've tagged Boeing as the start of a company and CC as the continuation of a company. And similarly, we have Wall Street, which is a location. Wall is the start of a location. Street is the continuation. And Mulally, the same thing happens again. So what I've basically shown you here is that we can take the named entity recognition problem and map it directly to a tagging problem where we're going to tag each word in turn in the input sequence. To develop a little bit more intuition for how we might develop a model for this problem, or what kind of information might be useful in developing a model, I want to talk about 2 different types of constraints that play a role in the part of speech tagging problem, or actually any tagging problem. So, and I'll call these different types of constraints local versus contextual. So local constraints take the following form. If we look at a particular word of English, for example, can, and again we're considering the part of speech tagging problem here, can has a preference to be a modal verb. Okay, so it's much more often seen as a verb in English, but it can also be seen as a noun. So a priori, can has a bias to have one part of speech over another part of speech, and we'll refer to that as a kind of a local preference, the local preference of a word to take one part of speech over another. But we have to balance these local constraints against what I'll call contextual constraints, which are that some part of speech sequences are much more likely than others. So as one example, a noun is much more likely than a verb to follow a determiner. Okay, so if I have a determiner, the tag is dt, this is a word like the or a. After a determiner, I'm very likely to see a noun, NN is a noun. I'm much less likely to see a verb. Okay, so there's sort of contextual information. Some tag sequences are much more likely than others. And we'll have to balance these two types of constraints when we build tagging models, and it's worth remembering that these preferences are sometimes in conflict. So if I take this sentence here, the trash can is in the garage, and if I consider this word can, then can has a local preference to be a modal verb, but it's clearly a noun in this particular context. And that's because the surrounding words, the surrounding syntactic structure dictate that this really has to be a noun in this context. So two sources of constraints, local versus contextual, and we'll see that we can build a model which actually balances these two types of constraints. So in hidden Markov models, the basic idea is the following. I have some input sentence x, which consists of n words. So each of these is a word. You know, this could be the, dog, and so on and so on. And I have some tag sequence y1 through yn. So this might be determiner, noun, and so on. And an HMM is going to define a joint distribution over over word sequences paired with tag sequences. So this is precisely an instance of the generative models I just showed you, in that if we think of a word sequence as an input and a tag sequence as a quotes label, we now have a joint distribution over these things. And this is a distribution over all possible word sequences x1 through xn, and all possible tag sequences y1 through yn, where these two sequences have the same length. Once we have defined a model of this form and learned the parameters of this model from a set of training examples, the output from the model is going to be so here I have an input x, which again is a sequence of words. The output for this sequence is going to be the sequence of tags y1 through yn, which maximizes this joint probability. So here I'm basically going to have a search over all possible tag sequences for the input sentence. I'm going to find the tag sequence that maximizes this probability. Now, this in itself is an interesting problem because the number of possible tag sequences grows very quickly with n. It's exponential with n. And so brute force search over all possible tag sequences is in general not going to be possible. But we'll see there's a very nice way around that problem for the class of hidden Markov models. Okay, so on this slide I've given a formal definition of trigram HMMs. So here I have the formal definition, and on the next slide we'll see an example which will probably help to clarify things. But let's go over this definition. I'm going to assume two sets. So V is going to be the set of possible words in the language. So it might contain, for example, the, dog, cat, a, box, and so on and so on. And I'll use S to refer to the set of possible tags. So for example, we might have determiner, noun, verb, preposition, adverb, and so on. Typically, by the way, we might have, I don't know, on the order of a few tens of tags. The Wall Street Journal part of speech tagging corpus I referred to earlier had approximately 50 tags. It can vary quite a bit by corpus and language, but that's not a bad estimate. Okay, so we have these two sets, and then a sentence is a sequence of words x1 through xn where each xi is in V, and a tag sequence is going to be a sequence of tags y1 through yn plus 1, through yn plus 1, where yi is in S for I equals 1 to n, and yn plus 1 is stop. Okay, so I'm again going to make use of this stop symbol, which we saw in the previous lectures on language modeling. And it's going to play a very similar role to what we saw in language modeling. So I've just extended our definition here. So our joint distribution is now over sequences x1 through xn, together with tag sequences y1 through yn plus 1. So this might, for example, be the dog barks, and this might be determiner nn vb stop. So notice I have this extra symbol at the end of the tag sequence. So how do we define this joint probability? So I have a product of two terms here. Here I have a product from I equals 1 to n plus 1 of qyi given yi minus 2, yi minus 1. Notice that this is very, very similar to what we saw in trigram language models. In fact, this, as we'll see very soon, is basically nothing more than a trigram model applied to tag sequences. So that's the first term. And the second term is as follows. I have a product from I equals 1 to n of e xi given yi. So the e parameters, for example, look like the following. We might have e of the given dt. And that basically corresponds to the probability, given that I have the tag dt, that I see the word the. So in some sense, the probability of the tag dt emitting or generating the word the. Okay, and I have one term for each word in the sequence. So the parameters in the model are as follows. I have a trigram parameter for every trigram of tags UVS, where U and V can be in the set S, and I'm again going to use the start symbol star. This is very similar to what we saw in language models. And S can be any member of S, or it could be the stop symbol. So that's the first set of parameters. These are basically trigram parameters. And secondly, for any word in the vocabulary and for any tag S, I have the conditional probability, or rather parameter corresponding to the conditional probability of X given S. These are often referred to as emission parameters. So two parameter types in the model. Given these parameters, I can then calculate the joint probability of a word sequence x1 through xn and a tag sequence y1 through yn plus 1 as this product of two terms. How do we apply this model to new test data sentences? And this is where we see the Viterbi algorithm come into play, which is a very famous algorithm. It's an example of dynamic programming, a critical idea from algorithms in computer science, and it's really a rather beautiful way of applying these models to test data sentences. So what's the problem that we're left with? It's the following. So we have some input sentence, x1 through xn. For example, it could be the dog laughs. And this is a new sentence, it's a new test data sentence, and of course I'd like to map this to a sequence of tags, for example, DNV. And to do that, I have my model. So this probability is defined by an HMM. through the parameters estimated from a training corpus. And the task is to find the highest scoring tag sequence under this model for this particular sentence, x1 through xn. Okay, so again, S is going to be defined to be the set of possible tags. Let's say for the sake of argument we just have these three tags here, dn and v. And so we're going to search over all valid tag sequences where yi is an S for I equals 1 to n, and yn plus 1 is equal to stop. We're going to assume that P takes the form I showed you for a trigram HMM. So this is this structure again. So just to recap, I have a product of Q terms from I equals 1 to n plus 1. Remember, yn plus 1 is always equal to the stop symbol. And then I have a product of E terms. So this is going to be terms such as E of the, given that I have determiner as the tag. So if we go back to this slide, the critical thing we're going to leverage in getting around this problem is that our probability distribution takes this form, and critically, these trigram parameters only depend on subsequences of length 3. So this model has a particular structure. And that will actually allow us to do search for the most likely tag sequence to solve this problem much, much more efficiently than brute force search. Okay, so now let's give some definitions underlying the Viterbi algorithm, which will be the efficient algorithm that solves these problems with brute force search. So I'll define n to be the length of the input sentence. So I have some input sentence x1, x2, x3 up to xn. And then a central definition is going to be this function r. So r is going to take a sequence of tags as input. So we always have star star as y minus 1 and y0. These are the start symbols. And then we could have some sequence of tags for y1, y2, y3. And so k is the length of the sequence. In this case, k equals 3. So r takes in a sequence, such as star star dnv, and basically calculates its probability under the HMM using what is basically a truncated expression. So we just have the first k terms, a truncated version of the expression we saw for full HMMs. So I have product I equals 1 to k over these q parameters, and a product from I equals 1 to k of these emission parameters. And so this is essentially a probability of just this sequence, which is of length k equals 3 in this particular example. Now we're going to define a dynamic programming table. So pi k uv is going to be the maximum probability of a tag sequence ending in tags uv at position k. Actually, to be completely precise, we need a couple of other definitions. So I'm going to define s sub k for k equals minus 1 to n to be the set of possible tags at each position k. So again, if we think about this input sentence, x1, x2, x3 up to xn, and let's say s is our set of possible tags, say d, n, v, p, then at any of these positions, 1, 2, and so on up to n, we have 4 possible tags, d, n, v, p. And at positions 0 and minus 1, we have a single possible symbol, star. And these definitions reflect that. So s minus 1 is equal to s0 is star. So the set of possible symbols or tags at positions minus 1 and 0 are just the star or start symbol. And for any k and 1 to n, s sub k is equal to s. So it's the full set of tags. So this notation will just make things cleaner when we give the full definitions. Okay, so pi k uv. K can take any value in 1, 2, up to n. U takes any value in sk minus 1 and v takes any value in sk. So this is going to be the maximum probability of any tag sequence ending in tags uv at position k. More precisely, pi kuv is, here I have a max over all sequences with k tags, y1 through k, preceded by y minus 1, y0. These are both star, always assumed to be star, such that yk minus 1 equals u, yk equals v of this R function I've shown you here. So to summarize, we have developed a full approach for the tagging problem based on hidden Markov models. Let's just go over some pros and cons of the approach I've shown you. One big advantage is that hidden Markov model taggers are very, very simple to train. It's simply a matter of compiling counts from the training corpus in the way I described earlier, and then deriving these simple maximum likelihood estimates or these simple linearly interpolated estimates. They perform relatively well. So, for example, for the named entity recognition task, in the work that I cited by Bickel and others from the late 90s, they performed over 90% accuracy in terms of recovering these named entities. So that's a pretty good level of performance. The main problem with these models is that, as I said, we have this problem of estimating these parameters E of word given tag. And we saw a rather heuristic method for dealing with low frequency, low count words by grouping these words into different classes depending on their spelling. And that's really a black art. It takes a lot of human intuition, human intervention in the problem. It's a rather clumsy approach to this particular problem, and it becomes increasingly difficult if the words that are input to the model are more complex. Later in the course, we'll see other tagging tasks where this approach really gets out of hand.